Okay guys, so I'm doing a video now on the boiling and melting points of metallic compounds and how you would answer an exam question to explain why metallic compounds have a high boiling and melting point. And for this question, for any question about explaining the boiling and melting point, you're going to go through the same framework in your answer. It's these 4 points here. So I am going to make other videos on the other 3 types of bonding, so ionic and the 2 types of covalent. So you can watch those after you've watched this, if you like this. So here's my 4 points I'm going to address. The first point is, what type of structure do metallic compounds make? Well, believe it or not, metallic compounds make giant metallic structures. And you get a mark for saying that. So giant metallic structures. The key word here, which everybody always forgets, is this word giant. If you just say a metallic structure or a metallic lattice, that won't be enough. You've got to include the word giant in there. That gets you the mark there. So, what type of structures make giant metallic structures? Just to go into a little bit of detail about what a giant metallic structure is, although you wouldn't necessarily need to write this down in your answer, if I have my metallic structure, what I've got here is, now I'm going to say atoms, I'm going to change this later, but let's say I have some metal atoms. When metals join together, when they bond, when they form metallic bonds, they delocalize their outer shell electrons. Now the number of outer shell electrons they delocalize depends on how many they have. So for example, group 1 metals will delocalize 1 electron, group 2, like magnesium and calcium, they'll delocalize 2. But all metals delocalize some electrons when they bond together. The word delocalize means to, so if an electron is delocalized, it is not stuck on one atom. It's being passed between them all. Imagine us all stood in a room together, passing pens amongst ourselves. The pens being the electrons and us being the atoms. So we're passing them all around. So all these electrons, they're not really on the atom, they've been taken away from it, they're not on it. So I'm just going to, on my atoms, I'm going to add just a few little minuses to represent all these electrons. It doesn't have to be equal to the number of atoms, that's fine. However, up until now I've been using the word atom. But as soon as these atoms lose the electron, it is no longer correct to call them an atom. Because if I lose an electron, I'm going to get a charge. So imagine, here's me, here's my negative electron. If I lose that negative charge, what am I left with? Well, I'll be left with a positive charge. If you lose a negative, you're left with a positive. So as these atoms lose the electron, they become ions. And that is the key word to say when talking about metallic bonding. There are no atoms in metallic bonding, there's ions. And they'll have a positive charge. Now, if it was a group 1 metal, they'd have a 1+ charge. Let's say it was a group 2 metal. Let's say it was calcium. So each of these will have a 2+ charge. You write that in all of these as well. This would be your diagram for metallic bonding now, with all the 2+ written in. So, what's actually holding it together? Well, as my ions, remember they're ions now, not atoms, as my ions are passing the electrons between each other, that causes an attractive force. So imagine here's one ion, here's another ion, and this pen is the electron. As they're passing them and sharing them, they're causing the ions to be attracted together. Definitely don't say this in the exam, but it's kind of like the electrons are the glue holding it together, but that's not what we'd say. What we would say is we have an attraction between these negative electrons and these positive ions. And whenever a negative and a positive attract each other, we call that an electrostatic attraction. Just something to remember. That's what we call it when a positive and a negative attract. So we have an electrostatic attraction. And what's it between? Well, it's between my positive ions. I'm going to underline the word ions, because if you say atoms, no marks. And have a think now then, what should the second bit be? Positive ions and what? If you said negative electrons, you would not get the mark. because it's not all of the electrons which hold them together. There's only a few certain electrons which kind of act like the glue and hold it together, and they are the delocalized electrons. So electrostatic attraction between positive ions and negative delocalized electrons. That's what holds it together, and this is actually a very strong force. So these negative electrons and positive ions are held very strongly together. And incidentally, the more electrons the metal can dissociate and delocalize, what effect do you think that has on the boiling and melting point? Well, it's going to increase it, isn't it? If I delocalize one electron, I've only got a few delocalized electrons acting like glue holding it together. If I delocalized maybe 2 or 3 electrons, then that's a lot more delocalized electrons holding it together. So as you go across the period, metals delocalize more electrons, which is also why, as you go across the period, the boiling and melting point of metals increases. So aluminium has a much higher boiling point than magnesium. Magnesium has a much higher boiling point than sodium, because that's as you go across. So, we now know what causes the force, but we don't know how strong it is. Let's write that down. This is strong. So this force is strong. This is a strong force. This force, you could also call a metallic bond. All bonds are forces, but not all forces are bonds. I'll talk more about this later. So you've got to be really careful with your terminology here. It is okay to call this a force. You could call this a bond as well, but really think about it before you write down the word force or bond, because they're not always the same. And so if I have a stronger force, or a stronger bond, that's going to require more energy to break. If I'm holding on to this not very strongly, it's not going to take much energy to break it. If I'm really strongly holding on to this, it's going to require much more energy to break it, and therefore I'll need a higher temperature to supply the energy. So therefore requires a large amount of energy to break. And that's it, that's your answer. That is metallic bonding.